Whenever you're ready, Anna.
Okay, perfect. Hello, let me extend a warm welcome to the NYU Tandon School of Engineering and the audience. Our seminar has proven to be an important and informative series in AI. The seminar series in modern artificial intelligence, now in its 6th year, is aimed at unifying scientific communities around the influential research ideas of today that we predict will have major impact tomorrow. AI is already recognized as an important topic of research with applications in medicine, biology, neuroscience, and other vital fields. We hope that the scientific discussions that result here will contribute to building a better world and promote groundbreaking discoveries. I'd like to thank Daniela Kovacevic for her strong support, as well as my own Department of Electrical and Computer Engineering for hosting this series, which has evolved into a significant event in the AI world. When I first conceived of the series in 2017, I hoped that I would be able to attract highly esteemed speakers doing revolutionary work in their respective fields. I say, with some humility, that I have succeeded beyond my wildest dreams. Our guest today is a wonderful example. John Langford studied physics and computer science at the California Institute of Technology, earning a double bachelor's degree in 1997. And he received his PhD from Carnegie Mellon University in 2002. Since then, he has worked at Yahoo, Toyota Technological Institute, and IBM Watson Research Center. And he is currently a principal research scientist at Microsoft Research, where he is working, as he says, to solve machine learning. The primary author of the popular machine learning weblog, Hunch.net, and the principal developer of Vocal Wabbit, he has a long roster of research projects to his credit, including ISOMAP, CAPTCHA, learning reductions, cover trees, and contextual banded learning. His presentation today is titled Discovering an Agent's Controllable Latent State, and it will explore the intriguing question of exactly how, given rich sensors like cameras and highly stateful environments, we can learn what an agent can do. I know none of us can wait to hear it, so without further ado, I give you John Langford.
Thank you, Anna. The picture on the first slide here actually tells the story of the talk. It was an experiment that we did where we had 9 different agents in 9 different mazes. We had an overhead camera looking down on all these agents in all of these mazes. So given the pixels from that overhead camera and given the actions of the agent in the lower right corner, we have an algorithm that outputs the graph on the right. And you can see that graph on the right kind of precisely corresponds to the latent state structure that the agent experiences as it moves around, the different locations that it can have. So that ability to kind of discover the configuration space that an agent can be in based upon complex sensory information with many distractors is, as far as I can tell, new in the world. I don't know anybody else has been able to draw a graph like this. So the talk is really about how this is possible and trying to give an understanding of a broader set of experiments and foundations for doing this kind of thing. I should say, please feel free to ask questions during the talk. I'm happy to discuss things. And there's somebody who's looking at the chat to help with this. Oh, and there's a website here where you can go and look at one of our papers, which is discussing this experiment and some of the others as well. Okay, so I'm first going to start with what are we trying to do? And the setting here is a little bit different from normal reinforcement learning, if you're familiar with that. We're thinking about a setting where there's the world, but there's also, agents and processes going on in the world. So there's something producing changes in the world that you don't really control. And then, there's observations which are maybe going to other agents or to other processes, and there's observations coming to you as an agent. And then based upon what you observe, you have some policy which has a set of possible actions available, and it chooses one of these actions. And then this process repeats over and over again, where you have observations, you have a policy, it chooses actions over and over again. But in addition, the world has other things going on in it, creating other observations. There are other changes that you don't control. And so that setting is that's repeating over and over again.
ఇదేంటి రావట్లేదు కెమెరా
Is there a
పోయింది
question?
ఇదిగో దిస్ ఇస్ iPhone 14.
So there's no reward. That's one of the big changes from reinforcement learning. And there's a bunch of other things that are acting in the world, which is another substantial change from typical reinforcement learning settings, if you're familiar with that. But other than that, it's just sort of a simple sequential decision-making type of setting. And I'm going to be thinking about sort of, so one way that kind of organize my thoughts about intelligence is in thinking about different levels of intelligence, where you have kind of a basic seek avoid, which is reinforcement learning. And then you have sort of a rich sensory and planning, which is, I think it was more advanced reinforcement learning. So we're thinking about the advanced reinforcement learning. And that is a picture of a hunting spider. So I wanted to give you a sense of what a hunting spider can do. Let's see. Right. Let me. This is from BBC. It's about a hunting spider that hunts other spiders. So it can look around. It has eyes. It can see. It can plan out a path to actually reach the spider that it's trying to hunt. And then, of course, you can start executing on the path. This is just a little tiny hunting spider. It's not very big at all, but it's capable of a degree of intelligence that it's kind of beyond the state of the art for us. It figures out how to get above the spider that it's hunting, and then it's going to lower itself down, and it's going to get kind of violent soon. So I'm going to turn this off. But the idea is that it can figure out in its environment. Let's see. Advance. Oops. Let me, there we go. Okay. So you can figure out in its environment where it is using its eyes. And
but it can be more general than that.
It can plan to reach some location. You can actually watch it planning. This is something which is just, again, like smaller than the tip of your fingernail. It can kind of explore, to gather experience, to learn. It can explore its environment effectively. And then there's another aspect which I think is kind of not understood until you start really dwelling with these problems, which is an ability to kind of ignore irrelevant parts of the environment. And so I want to show you another experiment that we did. This is an experiment with a robot arm. This is Rajan's robot arm. He built it as a hobby. We decided to try out the algorithm on the robot arm. So in doing that, we set up the robot arm. We gave it kind of a virtual maze to work with in terms of where it was allowed to move. And then we created as many distractors as we could. So we had a camera in the background. We have a bunch of birds that go up and down, a bunch of lights that turn on and off. And then, okay, so you see on the left there's the front view, and the middle is a top view. And on the right, we have a learned view where we're going to discover latent states, like in that image that I showed you at the beginning. And then based upon the latent state which is discovered, we're going to predict the observation. And what you can see is that the predicted observation incorporates none of the exogenous variation. There's basically just no change whatsoever. And furthermore, the mapping between the left view and the right view works even when we're like tearing apart the setup, which is not what it was predominantly trained on. So this degree of robustness in discovering kind of the latent structure is, I think, kind of exciting. It's a capability to work with real world complexity, which maybe we didn't understand how to do previously. Okay, so I wanted to stop here and ask, are there any questions about what it is we're trying to do? So if I was going to try to summarize what we're trying to do, I would say we're trying to do causal summarization. So we have this incredibly rich, megapixel camera coming at us. It's completely sufficient to tell us exactly where we are in our environment or things like that. But we're trying to figure out, if we try to make a policy which depends upon that incredibly rich sensory information, it may require an enormous amount of data in order to learn. So we're trying to figure out what is the sort of the minimal set of values which enables an agent to do all things. So in robotics, it's called all things is called the configuration space.
Join. I just joined.
Is there a question?
Hi, Professor. So there is a question that, like, what are some practical applications of this AI?
Yeah. So practical applications. I think you want to think about situations where the goal is really where it's necessary that you kind of learn an environment in an online fashion. So if I was going to think about situations like that, I would say so one that comes up with Microsoft is maybe you want to debug systems, right? So, and in particular, maybe you want to debug visual systems. And so what you really want to do is you want to explore all of the nooks and crannies of a visual system. And then the process of discovering this latent state structure that I mentioned does that exploration for you. And then maybe with a little bit extra work, you can discover bugs as well. And if you want to think about robotics, then maybe you would think about a disaster like Hurricane Ian, right? So the streets are completely different. The houses are essentially just gone. There's no like pre-known notion of what is where. And so you would like to have a system that can kind of discover what the new world looks like post Ian and actually maybe assist people in various ways. And then there's a more longer term application, which I think is around education, if that makes sense, or online tutoring. At present, machine learning gets used for online tutoring in kind of a, maybe which question should I ask next kind of way, where you can, I guess the reinforcement learning that gets used there is, I think, fairly minimal. But you can imagine a much more personal tutor that sort of through questions and observations explores to discover what a student knows, and then can come up with a strategy for helping them learn more. So these are all situations where you can't just use some big pre-existing data set in order to kind of pre-learn things. You have to actually interactively explore to discover what the problems are, or what the configuration space is, and think about how you can expand that. Does that make sense?
Yes. So, and there's another question from the audience that, like, from the previous slide, the input of the robot is the image from a camera, and it's an agent then like to ignore the videos in the background since it is irrelevant. So that's the question.
Yeah. So the videos in the background and the blinking lights and the dipping birds, none of them are things that the agent controls. And so because you only really care about how you can change the world, they get ignored.
Okay,
And
thanks.
John, just a quick clarification question. The agent has a camera installed on itself, right? So it sees the work through that camera, right?
It's not on the agent here. It's just an external camera.
An external camera. Okay, thank you for the
Yeah.
clarification.
So it's a third person kind of view.
Yeah, got it.
Okay, so
And finally, yeah.
go ahead.
And finally, there's a question from the audience that how much data is the algorithm need to learn that?
Yeah, so the data from all the experiments that I'm talking about today are on the order of a few thousand interactions. Right, and so that's it's more than as ideal for a robotic setting, for example, but it's within the realms of possible, and it's far less than millions of interactions, which you might be seeing in other reinforcement learning papers. Okay, so we want to find this kind of minimal sufficient set of values to enable an agent to do whatever it can do. Okay, so let's think about what kind of problem this is. It claims it's not a classification problem because, I mean, you don't know what the set of latent states is in advance. So there's no like given this, predict that type of thing that's defined. You have to kind of discover these latent states as you're working through things. And it's not a clustering problem, because if you're trying to cluster, then you know the kind of view on the TV or which lights are on, all these would become their own clusters, and so most clusters are sort of irrelevant. It's not a generative modeling problem, because we're not really trying to create a picture of the world or predict the sensor values that the robot will have, or the agent will observe later. Instead, we're trying to actually discard as much information as possible, right? So we want to go from like a megapixel camera with 10 to the 7 bits down to something like 10 bits. So that's kind of a very massive degree of information loss. And so there's a question of prioritization, which information are we trying to throw away and which information are we trying to keep? Okay, are there any other questions about what we're trying to do? Okay, so let's talk about how a little bit. How can you kind of learn to ignore distractions? So let's think about that robot arm we saw. There's a camera which is seeing it, and underneath or implicitly, the agent has just a relatively small set of configurations which we allowed it, right? So it just is 3x3 maze, so 9 different latent states. So the agent can move amongst these different locations with some sort of control. And then there's some, if you think about this as a game, there's some sort of effectively a rendering function that reality gives us. But this rendering function depends upon a lot of additional details, the place in the movie, or the timing of the dipping birds, or all of these other details. Okay, so that's the structure of things. And now let's think about an approach which doesn't quite work, but will be very helpful for us to think about an approach which does work. So an approach which doesn't quite work is a one-step inverse model. So the idea there is that you're going to predict the action given an observation and the observation before the action and the observation after the action. So if we're doing this, what does it look like? Well, suppose that we're given an observation from latent state 1 and an observation from latent state 2, and then you can predict that it must have been a right action, right? And then given an observation from latent state 5 and another observation from latent state 8, you know that the action must have been down. And given an observation from latent state 9 and an observation from latent state 8, you can predict the action must have been left. So this is what we're trying to do. And now this is the one-step inverse model. There's an issue which comes up with this approach, which is actually fairly commonly used. So let's think about just the 4 highlighted latent states, right? So A, B, X, and Y. Okay, so if we're in X and we see A, we know we must have gone up. Or if we're in Y and we see B, we know we must have gone up. If we're in A and then we see X, we know we must have gone down. If we're in B and we see Y, we know we must have gone down. Right. So if you have 9 latent states, you can kind of cover all the possibilities, and then you can achieve perfect accuracy in predicting the action. So that seems great. We're getting perfect accuracy. But suppose that we make a mistake in our labeling and we say, oh, look, the X and the Y are actually just one latent state that we'll call X. So we're thinking of these as both being the same latent state. Then it turns out that if you have X and then A, and then you know you must have gone up, X and then B, you know you must have gone up, A and then X, you know you must have gone down, B and then X, you know you must have gone down. And so with 8 latent states, we also have perfect accuracy. So this is kind of a very important point. We want a minimal sufficient summarization of causality. And the claim is that the inverse model inherently is not sufficient. It doesn't cause you to want to distinguish things which are clearly distinguishable. Other questions about this? So inverse modeling does not give us enough information to distinguish things that need to be distinguished. Okay, so you can kind of generalize this. You can actually get away with 7 latent states just by taking all those middle ones and declaring them all to be the same latent state. Okay, so this problem is real. If you take a look at, I mean, we're using this particular maze with a robot, and in theory, you have a worst case which aliases different latent states, as you see in the middle. And then in practice, when you actually go and you try to do an inverse model, you get a similar structure to the aliasing that happens between different latent states. Okay, so now the question is, how do we deal with this? Let's just do a thought experiment. Let's say that we start at latent state 8, and then we're going to move twice. So if I tell you that you end up in 4, then you know that the first action must have been a left. If I tell you that you ended up in 6, then you know that the first action must have been a right. If I tell you that you ended up in 5, then you know the first action must have been an up, or maybe a stay and then up, but you must have had an up in there. Okay, so that given that I observe one of the middle latent states, the 4, 5, or the 6, based upon its identity, I can determine the action. That ability to distinguish the action implies that I actually need to distinguish the different middle latent states, the 4, 5, and 6. And so driving for accuracy in this 2-step inverse model ends up causing us to want to distinguish between 4, 5, and 6. So that's kind of the essential observation from what is a multi-step inverse model. Okay, so the technique we're using here is a bottlenecked multi-step inverse model along this AC state. So you get an observation, you take an action randomly, you run the agent for k steps in the environment, and then you're going to observe something at the end, and you want to predict the action given the first observation and the last observation after k steps. Okay, so I showed you an example where the multi-step inverse model addresses the drawback of a simple inverse model. Let me tell you a little bit more about why this will work generally. So empirically, in theory, of course, it works on the robot, and empirically, it works on the robot. That's why we had that very nice video. Okay, so that's great. Okay, so you can kind of show in theory for particular settings that it will recover the full configuration space, the full latent state space using this kind of approach. The other thing which is very important is the bottleneck, right? So the F that we're learning here is constrained to have only a relatively small number of outputs on the order of 10 bits or less. So given that it has only a small number of outputs, you're forced to ignore a lot of things. And it's this kind of constrained output, the bottlenecking, which gives us the ability to discover or to ignore all of these other extraneous details that are not in our control. Okay, so before I go on, are there questions about the technique?
Yes, so there is a question from the audience that are there any requirements on the controllability of the system? For For example, if we go up, but the state change is right with some non-zero probability.
Sorry, if you go up, but what?
If you go up, the state change is right with some non-zero probability.
Yeah, so this can work with stochastic transitions as well, if you look at the theory. So there's a paper we have at Colt, which is not fully general, but which deals with stochastic transitions.
And another question from Professor Yashabangio, that how do the theoretical results depend on K? Is there a different requirement for K for different tasks?
How do the different results depend upon what? Say again?
Depend on K. Like you have, you depend on K actions, right?
Oh, yeah. So at least in terms of the theory, the amount of interaction that you need kind of depends linearly on the number of actions which are available. And in practice, we've only worked with a relatively small number of actions being available. However, it need not be a constant number of actions which is available. It could be that, you know, in some locations you can only have 3 actions, in other cases 8. Are there any other questions?
Yes,
Yes.
so there's another question that do the random actions guarantee the sufficient exploration? And can you give more details on the expert actions that you mentioned in the precedent?
Yeah, so random actions in general are not sufficient because it's easy to create an environment where random actions just fail to explore. I'll show an example of that later. And so in those environments, what's important is that you actually take your learned latent state structure and plan to reach the frontier, which we can do.
Recording in progress.
And another question is that, can you further explain how bottleneck remove irrelevant information?
Yeah, so the bottleneck removes information because it's forcing the system to just prioritize which information it has. So obviously you have to throw away a lot of information, and then through the bottleneck. And then if we go back to here, you see that because we're trying to learn the bottleneck while trying to predict the multi-step inverse action, the bottleneck is forced to prioritize the information which actually gives us the configuration space, right? So it must keep 4, 5, and 6 separate so they can give different predictions for observations from 4, observations from 5, and observations from 6. Okay, so let me show you.
There is one more question. Maybe I can just
Okay.
read out one more question. What if you need to model the parts of the world that you cannot control, like the movements of planets, to make sense of how the world works? An example, understand gravity in places that you can control.
Yeah, so that's not what this is doing. If you need to model more, then you need a different technique than what we're using here. There's several other techniques which I'll mention which do model more, but I'm not certain that, well, I mean, one technique is model everything, which is kind of what an autoencoder does. That may be too expansive for what you want, or maybe it's not. So we have to think about that a little bit. Okay, so let me show you a few more results. There's a question earlier about kind of a third person versus first person point of view. We also did an experiment with first person points of view. So we used the Matterport. This is a house where people took high resolution pictures at many different locations in the house. And then you can kind of connect these different locations in a graph that you can travel, where you can travel along the edges. There's also observations taken at different elevations within this graph. And so to make the problem a little bit harder, we randomized the elevation of the viewpoint. So the result was that using AC state, we could discover the controllable latent state quite effectively. And we could ignore kind of the observation viewpoint, which is what the blue is showing us. If you don't use a bottleneck, then AC state still does reasonably. If you look at these other approaches, so there's kind of a generative model approach and an autoencoder approach and a contrastive learning approach. I don't want to go into details about these too much, but what you can see is that they tend to be pretty good at discovering the latent state structure because the observations are nearly deterministic, but they're not very good at ignoring the exogenous noise, which is the viewpoint noise. So this can work with a first person point of view as well as third person. In addition, we did an experiment where we took a maze and we said, look, we're going to augment the set of actions available so that half the actions cause a reset to the upper left corner. And then if you use a uniform random policy, it never really escapes the first room because the odds of resetting to the upper corner are pretty high. And so after multiple steps, you have an exponentially small probability of not being reset. But if you use your learned latent state to plan to reach the frontier, then you can systematically explore the entire environment. And then there's some follow-up work that we did where we're playing around with offline reinforcement learning. We have sort of 9 different agents, each of these taking some actions. And based upon this, you can learn some representation. And then based upon that representation, you can try to optimize one of the agents to actually walk. And you can tell which agent this was in this particular case. So it seems like there's a natural value just associated with the representations that come out of AC state in terms of being able to achieve a relatively large return. And we compared with a number of different algorithms and compared the quality of these offline learned representations for a number of different algorithms. And then just to emphasize the point, we had these learned latent representations for the robot, and we went back and just showed that you can actually have the robot trace out the perimeter of its learned latent state structure. Okay, so now switching from experiments to the theory. I haven't really emphasized the theory here very much because it gets sort of detailed, but there's a fair bit of theory discussing various details here, right? So we have a paper talking about what happens when the dynamics are deterministic. We have one talking about stochastic dynamics with structured observations. There's the AC state paper itself, which has an asymptotic analysis. There's also this learning with offline data that I mentioned, and there's a fair bit of work around continuous linear dynamics that we've done previously. The experiments that I talked about are, I think, beyond what we have fully understood theoretically, but there's ongoing work to understand what is possible theoretically. Okay, so are there questions about the experiments or where we are in terms of trying to understand latent state discovery?
Yeah, so there's a question from the audience that is there a notion of suboptimality on the derived state spaces? Do we need to find the true state space or partially correct spaces that lead to suboptimal but good policies?
Yeah, so is there a notion of suboptimality in the state spaces? Certainly you can imperfectly recover the latent state space. And for the offline RL experiments that I mentioned, that's the case. We're not actually trying to do things perfectly, because I think in an offline setting, you can't necessarily succeed even without good data coverage, which you have no way to control in an offline setting. So when you have an imperfect latent state, it still seems like you can learn, you can just do effective things with it. Another example of this is for that maze with resets that I showed, right? So in the beginning, your latent state is terrible, but it's good enough for you to actually reach the frontier and improve the quality of your latent state structure. Okay, so
there's another question. Does this work well in the latent states are more continuous, if the latent states are more continuous?
Yeah, it's a good question. So the offline RL is something where we did something with continuous latent states. It does something useful. I think that our mastery of continuous latent states is not very good yet. We're working on that, but that seems like something where I expect to see serious progress in the future. So I want to just another question.
Another question is, what is the latent space to discover the maze case at the beginning?
What is the latent space that you discover at the beginning?
Yeah, the maze case, the maze discovery case.
Yeah, so I mean, we discover one agent's latent state space at the beginning. So it's all positions in the maze that the agent can be. So I just have a couple things to finish up. I wanted to sort of give a sense of where things are. So we have this multi-step inverse criteria, and that seems to be a sweet spot in terms of being sufficient for latent state space discovery is an objective, but also minimal. I discussed inverse models where there's too few latent states. There's also approaches which are around reward-based latent states, like mu0, if you're familiar with that. So these approaches in general can be useful, of course, but because they're focused on the reward and they only distinguish latent states that have different rewards, they don't give you the same sort of foundational agent model, which is able to optimize for any reward function relatively easily. There's this sort of notion of bring your own latent, where you just impose a bunch of self-consistency checks. It's not super clear. Maybe that's not enough. Maybe it's too much. It's a little bit vague. There's two other approaches which I haven't really dealt with or dwelled on very much. One of them is the contrastive learning approach, where you find latent states that are sufficient to distinguish causal from acausal sequences. This tends to actually produce too many latent states because there are a lot of things that are observationally non-causal, which you don't control. So this may be useful for the gravity example, for example. So things which gravity, you may not be able to control an apple falling from a tree, but you can certainly set up a sequence of images for things falling from a tree. And you can detect whether or not two things are in sequence or not. And then beyond that, there's kind of the autoencoder notion of latent states, where you find the latents that are sufficient to predict the observation. And of course, that's even more expensive than contrastive. You're trying to model everything about what you observe. So this is a little bit of context compared to other criteria people have experimented with. And then I also want to say there's a lot to do in terms of expanding this into kind of a widely useful technology. Many of our experiments are not kind of done in a real-time fashion. So obviously getting the software together to do that and some changes to exactly how we learn could be helpful. There's a question about continuous latent states. It's very relevant. There's a project going on around that right now, but you know, this is honestly a fair bit to do. There's also combinatorial latent states. So if you look at my desk, there's like far too many things on my desk, and they can be in many different configurations. It's a combinatorial structure. Modeling that with discrete approaches would be ruinous. And then there's a notion of hierarchy, which seems very natural to think about. If I'm commuting into the office, I don't think about every step that I take on the way. How do you actually create that kind of structure naturally through objectives? Not entirely clear to me. All of these seem very important in the longer term in order to succeed effectively. Another thing which seems really important is if you think back to that hunting spider at the beginning, it didn't have to actually physically explore everything in order to understand the latent state space. Instead, it could look at what was around and kind of predict what the latent state structure would be. So that ability to project from your sensors into not just your current, but not yet experienced latent states is something that I think we need to develop at a learning level in order to really take advantage of this kind of approach effectively. And then I mentioned kind of online tutors or computerized tutors. I think that would be really great to do, but it's vague in my head exactly what the right latent state representation for dialogue should be. It's certainly the case that in dialogue, you are exploring and you are constructing some kind of understanding of where the other person's at. But maybe I need to learn more, but I don't know a good way to think about the representation of that in a manner which is sufficiently flexible to handle real world dialogue. All right, so oh yeah, we are indeed hiring. We have an intern rec up right now and hopefully more shortly. There's many people at MSR who have worked on this project. And then there's also many other people who were at MSR or interns or things like that. Other questions? So this picture still kind of really tells you what's going on, right? So we can, given the overhead view with all the distracting agents doing their things, if you have the actions of one agent, we can discover the latent structure of that agent.
Can you discuss a little bit about the applications of where you guys applied or want to apply this work?
I mean, we're certainly thinking about sort of visual interface debugging type of situations. That seems like it's a very natural application at Microsoft. I mean, it's always sexy to play with robots. Those are a lot of fun. I think we're still a ways away from having a practical application there. And I would really love to get to that kind of online tutor-like situations, but that feels like more like a 5 or 10 years ambition rather than a next year type of thing.
Any questions from the audience? We had quite a few questions during the talk, but I want to ask if there are any questions from the audience. So the question from the audience is, what is the most challenging aspect when you conduct this research?
Most challenging aspect when you...
I guess to interpret the question a little bit, what were the major challenges that you have to encounter during this research?
Oh. Well, I think there's kind of two key things. One of them is we really started with the theory and tried to drive towards the empirics in this case. And so, that often involves different expertise. So I'm very grateful for people who helped us along the way. And then the other thing, which I think was, a substantial challenge, is just that the idea that we could create a graph, a picture like this, is something which has been done in the world before. And so you have to kind of understand the possibilities based upon maybe the theory in order to think perhaps about even doing something like this.
So may I ask on the theory side again, can you kind of summarize what the theoretical description do you currently have of your approach, and what are the limitations in terms of potentially generalizing this theory?
Yeah, let's go back to the theory slide. So when the world is deterministic, it's relatively straightforward. So deterministic and discrete latent states. If it's stochastic, then we know how to do it with structured observations for a particular structure. That was what we had at this cold paper. We kind of know that it works asymptotically, which is an analysis in the AC state paper. That's on arXiv. And then we know that we can handle continuous for certain special cases, like a global linear dynamics, for example. Even with a rich observation, we can discover that and make things work. But the experiments that I was showing you are often beyond this. Like so for example, we're dealing with stochastic dynamics without having that kind of particular structure in the observation, or maybe we're dealing with continuous dynamics which are not fully linear, or not globally linear. So figuring out how to deal with each of these things theoretically, I think may give us some real insights in terms of shaping how we want to do things experimentally.
Okay. Let me just one more time, if there are any more questions from the audience. I know that there were plenty of questions that were asked throughout the talk, but this is the last opportunity to ask questions. Okay. So if there are no questions, then I will wrap up for now and let you go for a break. And then after your break, you will have meetings with students. Thank you so much, John, for your talk.
Yeah. Thanks a lot for organizing this, Anna, and thank you, everyone. Hope this is I consider this a very exciting direction, and I'm really looking forward to what we learn in the future.
And the link to the papers, if you can just remind one more time, was it provided on the first slide? Oh, here it is. Okay, perfect, wonderful. Thank you so much, and see you after the break.
All right.